So let's discuss about the active methylene group. The methylene groups is basically CH2 group. Carbon having two hydrogen is commonly called as methylene group. This particular methylene group will be considered as highly active or active depending on presence of electron withdrawing groups about the carbon. The carbon atom having two hydrogens is called methylene, and due to the presence of two electron withdrawing groups, it's called active methylene group. Now the question is that what are the active groups that may be attached to the CH3 group? For example, if it is NO2 is attached to the both ene, then it is called active methylene group. Similarly, if it is having aldehyde or ketone, if it is hydrogen, then it will be aldehyde. If it is alkyl group, then it is called as ketone. So presence of aldehyde and ketone about the carbon is called as active methylene group. Similarly, presence of OR groups, which is called as ester, due to presence of OR group about the carbon, it is called ester. So presence of ester group can also create the methylene group to be highly active. Some other compounds which are also can be considered are C triple bonded N means cyano groups, followed by amide. It can be 1 degree, 2 degree, and can be other. Okay, this one is called amide. Amide linkage can also create an active methylene group, and some others even in place of carbon they can be sulfur also. Now let's discuss about the molecules or compounds having active methylene group. Here we will discuss two compounds. These are acetoacetic ester and malanoic ester. So acetoacetic ester and diethyl malonate will be based on the group attached to the ketonic groups. What would be the ketonic group? If you see, this one is a ketone. This one is ketone. C double bonded O, both side carbon, so hence it's a ketone. And this one is ester. Now, depending on the group Z which is attached to the ketone will be considered for naming acetoacetic ester and malanoic ester. When the Z, that is the group, is a methyl group, that is CH3, it will be look like this one, and it's called acetoacetic ester. It's called acetoacetic ester. This one is called acetoacetic ester. If I replace the Z by group of say ester or OR group, R can be CH3 also, CH3, C2H5, etc. So here it is the oxygen, here it is a methyl group. So here it is the group, that is the OR group. This is the oxygen and this is the R group. So OR group that has remaining portions will be same, OED. So this particular group from heat condensation reaction. Here an Esteric group, say CH3, C, double bonded O, C2, H5. This one is an ester, say it's an ester 1. React with another ester of having a alpha carbon group, double bonded O, C2H5. The same ester can also be used, but condition is that it should not contain only one alpha hydrogen. If it is containing one alpha hydrogen, it will not undergo Claisen condensations. So here it is say 2. Here can be R also. Since I am considering the same group, that's why I just write it CH2. These particular hydrogens with the SO2H5 or the alkoxide part will be removed in presence of sodium ethoxide NaOC2H5. This one will be the first step, followed by ACl. It will give CH3, C, double bonded O. Then here it is oxygen and C2H5 will be removed with the hydrogen. So product will be C2H5OH. The remaining part from here, that is the CH2, will be here. This one is the CH2 from here, followed by double bonded O, followed by O, C2H5, which is considered as the beta. This one is the alpha. It is alpha, it is alpha. Here it is beta. So it is also called beta carbonyl ester, or it is called active methylene group. It is the way to prepare the compound. Properties of the active methylene groups. Active methylene groups can undergo reduction either on the ketone, that is C double bonded O, the left hand sided carbonyl part, CH2, this one is a ketone, or ester. Here it is the ester part. So that means reductions can be possible either in the ester groups or in the ketonic groups. Okay, or in the ketonic group. Basically, the reductions takes place in the ketonic group commonly. CH5, CH3. On reductions, say I am place reduction sodium amalgam. When I add sodium amalgam, it will reduce the ketonic carbonyl compound, the carbonyl compound. Carbonyl compound means C double bonded O. So this one will be reduced. Reductions means addition of hydrogen in expanse of an double bond. So if I break out the carbon oxygen double bond, and here it is the bond. Oxygen, one hydrogen will be with oxygen, another one will be done with the carbon. If only one double bond is broken up, it is called partial reduction. Partial reduction. And if it is break out completely, then it is here, this one is broken, this one is broken. So due to the broken up of both the bonds of carbon oxygen, one hydrogen will be here, another will be here. So carbons will get the 2 hydrogen. Similarly, what happened to the oxygen? Oxygen also intake and also take up 2 protons to lead to water. As it got completely reductions, so hence it is called complete reduction. Complete reduction. For partial reductions, we will use sodium amalgam. So product will be CH3, COH, H, CH2, C double bonded O, bond O, C2, H5. As the active methylene groups, this can be written as that way. So which is ethyl acetoacetate C2H5. It should be C2H5. Due to the presence of 2 acidic protons, 2 acidic proton, they can be replaced up by a base. Since they are the acidic, due to the presence of electron withdrawing groups, the carbon hydrogen bond will be weaker. Weaker means they can be easily break up, and due to breakup of carbon hydrogen bonds, hydrogen can be loosed out easily. As it aids to release the hydrogen ion or the proton, these are highly acidic in nature, which can be existed only and only if there is an electron withdrawing groups. So since double bonded O CH3 is an electron withdrawing group, and similarly diester linkage is here, and this one is also an highly active electron withdrawing groups. So resultant methylene groups will be highly acidic. By applying a base, for example NaOR, means sodium methoxide like that. So such compounds, when I apply it on the active methylene groups, it will lose out the hydrogen from here, since it will abstract out a base OR minus. From here I will get OR minus, which will abstract the hydrogens, leads to breakup of electron bonds to the carbon, and hence it will give a carbon ion in the following manner: COO C2H5. This is the one hydrogen still left out. Okay, if I applied another alkyl halide groups, or applied an alkyl halide, it can undergo acylations. It's called acylations, and leading to formation of compounds as shown below. For further reactions, I can apply sodium alkoxides, or stronger bases such as tertiary butoxides and etc. So again, if I applied any base of stronger base, it can be sodium alkoxides or it can be tertiary butoxides. It can lead to release of the remaining acidic hydrogen here, leading to another carbon ion, which further undergo reactions with an alkyl halide can lead to double substitutions, dialkyl substitution reactions. So that means R, C, CO, CH3, here it is say R dash, and CO, C2H5. So this is the basic way. from ethyl acetoacetate, synthesize pentane, that's 2,4 dash dione. Okay, you are being asked to prepare ethyl acetoacetate to pentane 2,4 dione. EA I will be denoted as EA. Pentane 2,4 dione. So 1, 2, 3, 4, 5. So pentane 2,4, 2, 3, 4, 2,4 dione. You have been asked to prepare these sorts of compound. First, let's write down the ethyl acetoacetate. So this one is the ethyl acetoacetate. When ethyl acetoacetate is treated with sodium alkoxide, for example, sodium ethoxide, it will lead to remove the most acidic protons, that is the alpha hydrogen. So here it will be the compound one hydrogen will be left out in expense of sodium. So sodium plus, here it will be the minus. On the very next step, when I placed out CH3, C double bonded O, Cl, Cl and Na will be removed as NaCl and leads to formation of another compound as follows. C, here it is the double bond followed by carbon, that is a CH3. So 1, 2, 3, 4, 5. So pentane 1, 2, 3, 4 dione. So now you have to remove out this particular group. So for removing it, you need first hydrolysis, that is by HCl, and secondly heat. When we heat, it is the ester will on acidified, the ester convert to their respective carboxylic group. Carboxylic group, when heated, it lose out carbon dioxide to give, and simple decarboxylations will take place. So hence our product will be this one. This one will be the product, which is the pentane 2,4 dione. We need to discuss another one, that is ethyl acetoacetate is converted to 3-methyl pentanol. You have been asked to prepare 3-methyl 2-pentanone from ethyl acetate. So let's first draw out the ethyl acetate, which will be, this one is the ethyl acetate. On treating with sodium alkoxide NaOC2H5, it will lead to form, this one is the minus Na plus. Now 2-pentanol 3, right? So that means how many carbons is still needed to make out to pentane, to convert it pentane. Now 1, 2, 3, so that means 3 is already there. I need 2 more to get pentane. So that's why I will add C2H5Cl. On adding of C2H5Cl, it will lead to form C2H5. So C2H5 will be here. Cl, take up the sodium plus and lose out as minus NaCl. the formed compound, since it is 3-methyl, I need 1, 2, 3. Here I have to add one methyl group again. Now I can remove it. If I removed 1, 2, 3, 4, 5, so pentane 2,1 can be already done. So now for preparation of 3-methyl, I will repeat the same process by applying another base. This time the base should be stronger one. For that, I will place potassium tertiary butoxide. Potassium tertiary butoxide will be the. So if I add it same way, the hydrogen, which is 1, 2, 3, so remaining there is a 1 hydrogen which will be lose out. K plus. So this one is the way. And the very next steps, I will place CH3Cl. Here it is the methyl CH3. Now the same process for conversions of ester to the respective carboxylic acid, and then heat out to decarboxylations. 1, 2, here it is the way. So I just remove this one and then I just make 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then 1 is here. So here it is. So this one is the 3-methyl 2-pentanone. Hope you understand the technique to convert ethyl acetate to any acetone containing part or any ketonic part. So first, always try to find out the respective alkyl halide which is needed to prepare the one. So this is the way. Similarly, there is one more. Let's discuss another example. From now onward, you can carry out all the conversations related to the questions like conversions of ethyl acetate to respective 2-methylpentanone. It can be 2-methylpentanone, it can be hexanone, it can be many, it can be anyone. So such types of conversions can be carried out in the shown manner. Similarly, if there is a questions to prepare 3-butyl, so this time the question is 3-butyl to heptanone. It is heptanone. So I have to prepare first. I will try to prepare 2-heptanone first. So first I just write down the ethyl acetate. The formula is this one. I add sodium ethoxide. So product will be this one. And plus. Since it is heptanone 1, 2, 3. So only 3 will be there. Don't consider the esteric part. So 1, 2, 3. So remaining 4. So that's why I will place an alkyl halide having 4 carbon atom, which is the butyl chloride. On addition of C4H9, the product will be 1, 2, 3, 4. 1, 2, 3, 4. So this one will be the product. So now find out whether it is heptane or not. 1, 2, 3, 4, 5, 6, 7. So we have prepared 2-heptanone first. Now here it is 3-butyl. So I have to make out 1, 2, 3. It will be always 3. Remember, this one will be always 3, and ketone will be always 2. Okay, so now I just place tertiary butoxide. Tertiary butoxide CH3. Tertiary butoxide will be this one, COK. So on applying tertiary butoxides, the product will be this one. Here it is minus, and K plus will be here. It will be K plus. And on applying 3-butyl, so again C4H9Cl. You can get the same base component, that is the sodium ethoxide here, but sometimes it is preferred to give the stronger bases since it is hard to remove the acidic proton. So here it is the product. One, 2, 3, 4. 1, 2, 3, 4. So this is the product. On hydrolysis, acidic hydrolysis followed by decarboxylation, the product will be this one. The ester will be gone up. So here it will be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 1, 2, 3, 4. This is the 3-butyl 2-heptanol. It's a simple way to prepare 3-butyl 2-heptanol. Now it's time to deliver for you. Now I just asked to prepare. First, you just try to prepare 2-pentanone. Now carry out this work on your own. 2-pentanone. One more is 3-propyl 2-hexanone, and try to prepare 4-phenyl 2-butanol. Okay, these are almost the same techniques you have to be on through. So try to find out the required way to prepare this. Other compounds can also be asked to prepare. One was ethyl acetate to succinic acid. Ethyl acid to succinic acid. How to prepare, how to convert ethyl acetate to the succinic acid. So again, the same way we just prepared. First, just write down the ethyl acetate. This is the ethyl acetate. You have to give a base NaOC2H5. So lead to, sorry, here it should be CH2. Here it is minus, sodium will be plus here, and on the very second step, since succinic acid, the formula of succinic acid is this one, CH2 COOH, CH2 COOH. So 1, 2, 3, 4. So I need 4 minimum. So here it is the way. Give Cl followed by CH2 COOC2H5. If I apply the compound, then our product will be here. It is CH2 will be here, COOC2H5. Now if I hydrolyzed it out in presence of a base, say NaOH, and second or H2O oblique H plus, it will be in the way now. So So which CH3, C double bonded O, and OH will be here. So it will break out like that. And one C2H5OH, 2 molecules of C2H5OH, one from here. Alcohol will be one is generated from here, another one will be generated from here. So this is the preparation of succinic acid. Succinic acid from diethyl malonate. So here it is the C, diethyl malonate, COO C2H5, COO C2H5. Given base sodium ethoxide C2H5 ONA. Most acidic proton will be removed by the sodium, so this one will be plus, this one will be minus, rest will be as remains same, COO C2H5, one hydrogen will be left out, this one is the hydrogen. Now I am placing an compound Cl CH2 COO C2H5 H5. Then this one will be removed. COO C2H5 will be here. Here COO C2H5. This now this particular CH2 groups will be here. This one, and then COO C2H5 will be here. This is the groups which I have joined it. Okay, I can write it in this manner. CH, let's compile up these two. COO C2H5 whole 2, and here it is CH2 COO C2H5. Okay, let's hydrolyze it. Basic hydrolyze. Give one another base, so KOH, and secondly acidic in presence of acid. So what will be the product? Both the ester will be converted to respective carboxylic acid. So CH COOH whole 2, and then CH2 COO. Yes. Just hydrolyze the ester. When I heat it out, around 150 to 200 degrees centigrade, it will lose the carbon dioxide, and hence the ultimate product will be CH2 COOH. Only one carboxylic groups will be left out, since this one will be CH2 COOH, which is the succinic acid. Alpha methyl succinic acid. Same way, you just prepare CH2 for diethyl malonate, COO C2H5 COO C2H5. At the base, that is sodium ethoxide, NaO C2H5 will be added, so that product will be Na plus CH minus followed by COO C2H5. Here also COO C2H5. And then for methyl, as I said, CH3Cl, so that here it will be CH3 in place of sodium, and COO C2H5 COO C2H5. Hydrogen will be is, for example, potassium tertiary butoxide, CH3 whole 3 COK plus minus. So hence that hydrogen will be removed, and it will be as C2H5. Here it is minus, and K plus will be here, C2H5. Br CH2 COO C2H5 I have given, so that potassium will be left out. COO C2H5. Here it is CH3. Here it is CH2 COO C2H5. Here it is COO C2H5. That one will be the product. And the very next step, as I said, hydrolysis H plus H2O. All the ester groups, all the esters will be converted to carboxylic acid. So CH3 C COOH, CH2 COOH, COOH. So this one will be the product. So when we heat it out, it will give CH3 CH COOH, okay, and CH2 COOH. This one, only one acidic groups will be removed, and hence it's this one will be CH2, or simply we can write it as CH2 COOH CH2 COOH. Sorry, this one will be only one. So here it is, since methyl is there, so this one is the methyl group. Convert diethyl malonate So now discuss about how to convert diethyl malonate to N-hyaluronic acid. So first draw the diethyl malonate. So here it is COOC2H5, COOC2H5. Just like earlier, the sodium ethoxide C2H5ONA. Compound will be CH2, C in place of H. It will be converted to Na plus. And COOC2H5, everything will be remain same, COOC2H5. When I add then C3H7Br, it will lead to form C3H7 will be here, acidic proton, let's be here, COOC2H5 down COOC2H5. Okay, what would be the next step? Next step I just add, and that is KOH, which will convert the esteric group to carboxylic acid, followed by the salt, that is C3H7 CH COOK COOK. Okay, so in the next step I just said HCl. On addition of HCl, C3H7 CH, these two groups of acid will be converted to COOH whole 2, and which on when heated 150 to around 200 degrees centigrade, it will lose out the carboxylic group, so that one carboxylic group, that is C3H7 CH CH2, this time COOH. So here one carboxylic group have to be left out. So what would be the product? 1 2 so it is this. If I draw the success, so this one will be CH3 CH2. So here this is from here, and this one is C3 H7 then CH2, then COOH. So this is called NBALE valeric acid, which is actually pentanoic. Methane, ethane, propane, butane, pentane, that is the pentanoic acid. There is equations to prepare crotonic acid from ethyl acetate. So let's go to prepare crotonic acid. So here it is the ethyl acetoacetate, C2H5. Here I just place acetaldehyde, CH3C double bonded OH. These two hydrogens will be lose out with oxygen as a water. So here be the product CH3C double bonded O, C double bond C, CH3 and H. This one is the part of the aldehyde one. The remaining part will be remained as it is. So this is the product. On the very next step, as I said, NaOH, sodium hydroxide, and H2O oblique H plus, which will lead to convert the ester to the carboxylic acid as well as so what will be the product? CH3 CH double bond CH COOH, which is called crotonic acid, plus C2H5OH. Here from C2H5OH alcohol will be here, and CH3, and this one is the CH3 here, CH is here, double bond is up to here, then C double bonded O, and this portions will be breakout, so it will be CH3COOH. So this is the compound. Sometimes there will be questions on preparing some cyclic carboxylic acids. So for example, cyclobutane carboxylic acid. This one is asked to prepare from the diethyl malonate. So first draw the diethyl malonate, CH2 COO C2H5. Here also COO C2H5. First, as usual, base. I have to add the base C2H5ONA, which will remove the most acidic proton, and a plus. H will be here. Here COO C2H5. Here also COO C2H5. Then, if it is cyclobutane, then you just say it. Since it is 4, butane is 4, so here it will be 3. If it is cyclopentane, then it should be 1 less, that is 4. And if it is cyclopropane, then it should be 2. I will add CH2 2 and followed by Br2. So here it is, since it is CH2 3, I have to add 3. So which will lead to remove the Br, and it will be as it is CH COO C2H5 COO C2H5. How many CH2? Since 3, so it will be 3. 1 Br will be here. Since this one is the acidic, it can undergo the same process, and it will be, this time it will be intermolecular. So first add a base, that is the highly basic. So potassium tertiary butoxide, CH3 whole 3CO minus K plus. So this is the potassium tertiary butoxide. And so on the very second step, this Br will be added here. So acid will be removed. So hence the product will be look like this one. Carbon up COOC2H5 and then CH2 whole 3, it will adjust to here COOC2H5. So this particular group can be drawn as 1, 2, 3, 4. So hence it can be drawn as 1, 2, 3, 4. 2 C2H is, so hence COOET, COOET. ET means ethyl. So which on acidic hydrolyze H plus oblique water, it will lead to carboxylic group. So COOH, COOH. Okay, and on when heated, if I heat it, it will lose one of the carboxylic group and lead to cyclobutane carboxylic acid. Now let's just try out the same way to prepare cyclopentane carboxylic acid. And secondly, prepare cyclopropane carboxylic acid. Just remember, for pentane H2 Br2, right? So N, value of N should be 1 less, that is N should be 4. For here N should be 4, and if it is cyclopropane, N should be 2. Okay,